PC Calculus, Lesson 9.3, Relative Rates of Growth. This is not too complex a lesson, although it can lead to some complex things. We're talking about rates of growth, getting bigger, so we're restricting our work to functions that become and remain positive. They can start negative, but they got to go up immediately. Generally speaking, all of these functions will start positive and stay positive. The fastest and the slowest growing functions, if you put them on a coordinate plane, are some variation, because this changes, of e to the x, or any a to the x. A polynomial, which we'll represent here as x to the n. In this case, it's x to the first, but it could be a x squared, x to the third, x to the fifth. And then the slowest one is log of x, any base. So that's the beginning, middle, and the end. So it actually answers almost all the questions we need to answer today, but we'll just start with those. We can use these to define how they grow compared to each other. If we compared e to the x to x squared, we'd get 0. So this means that f grows faster than g. If you just literally flip them, you would get the infinity. That's what's going on here. So, pardon me, I had it backwards. If f grows faster than g, you get infinity. If you flip them, you would get 0. So you can do it either way. There's advantages to doing one over the other. If they grow at the same rate, they come out to some constant that is not 0. That's where this gets a little bit confusing. A lot of people say, hey, I got a constant 0. Like, no, that's not a constant. A constant's 1/2 or 4 or 10 or something like that. So as in all things, let's just go. I'm going to put x on top. No, actually, I'll put 2x on top. Limit as x approaches infinity of 2x over x. Well, we can just simplify this before we do anything else. We don't have to get into L'Hopital's rule or anything. It just equals 2. This seems extremely counterintuitive to some people. Because, hey, I'm doubling this one. It should grow a lot faster. No, they're growing at the same rate. And if you think about their slopes, it'll make more sense. But regardless. What if L equals 1, then their end behaviors are the same. And each function is the right hand end behavior. Of the other. It's another one you have to actually stop and say, wait a minute, let me think about that. And sure enough, it works. We would just call that right hand behavior. So how do we compare whether e to the x or x squared grows faster? We'll just do what I just did. Take the limit. Let's put x squared on top. By the way, I have this horrible habit of making this a 0. Just, I don't know what it is. See if I did it up top. No, I didn't. Happens all the time. Watch out. If we do this limit, we get infinity over infinity. So we do what? L'Hopital's rule. Derivative. Well, that still equals infinity over infinity. One more time. 2 over e to the x equals, as I'll write it all out this time, the limit as x approaches infinity of 2 over e to the x equals 0. So we can say that e to the x grows faster. How about natural log of x and x? Again, I would put natural log of x on top. And I'll put it on top. Doesn't really matter. I've done this different ways. We get infinity over infinity. Derivative, we get 1 over x over 1, which is 1 over x. And the limit as x approaches infinity equals 0, so x grows faster than natural log of x. Doing it again for x squared and natural log of x, and I've decided to keep natural log on top. Now I'll put it on the bottom. Let's see what happens. That's infinity over infinity. That's 2x over 1 over x, which equals 2x squared. The limit as x... Gotta fix the one above. I don't like that. Limit as x approaches infinity of 2x squared, of course, is infinity. So x squared grows faster. And we'll fix this limit of 1 over x equals 0. Show that x grows at the same rate as x plus sine of x. So again, same rate, we should get a constant. Limit as x approaches infinity of, I'll leave it on top because it should not matter, over x equals infinity over infinity. So we plug this in and get actually we don't do L'Hopital's rule. We do x over x plus sine of x over x. It's tricky. A lot of people want to just do L'Hopital's rule every time. It would work here, but yeah, regardless. 1 plus, I do happen to know that's the limit as x approaches infinity, sine of x over x is also 1, so we'd get 2. Oh wait, my bad. I was thinking of sine of x as it approaches 1. As x approaches infinity, it's 0. So we would get 1. So they're right-hand end behaviors of one another. Lots of different ways you can do these problems. That's as good as any. So show that log base a of x, log base b of x grow at the same rate as x approaches infinity. So off we go again. These are infinity over infinity. Take the derivative. I believe it's natural log of x over natural log of a over natural log of x over natural log of b. These cancel. And I get natural log of b over natural log of a. So they grow at the same rate. We have a transitive thing here. Long time no see. If a, then b, and if b, then c. Then a, then c. So we can play with it that way, and so on and so on. It pops up every now and then. Let's show that these grow at the same rate. Limit of, we'll put f of x over now, way back when we did limits, we'd say, well, this one on the bottom is root x squared, so that's x. This one on top is x squared, so I would say the whole thing is going to be 1 over 4 when I'm done. But let's see what happens. We're never sure. Get infinity over infinity. Yes, it keeps getting bigger and bigger. See lots of different ways this is being done. You can actually distribute out the bottom, see where that takes us. I'm not sure if I want to do that, if I want to take the derivative. I gotta think about it. Here's what we're gonna do. We know that if we put in, just to show the transitive thing, h of x equals x. That's what these both end up equaling. I can show that, I'll put it in color. We'll do f of x first. Limit as x approaches infinity of root x squared plus 5 over x, make it x squared and a square root, would be x squared plus x squared 5 over x squared, which is square root of 1 plus 5 over x squared, as it goes to infinity, is just 1. And I could also do the other one. I gotta get a new color going here. Limit as x approaches infinity of 2 root x minus 1 squared over x equals 2 root x minus 1 over root x, which if I squared, I get that, which equals, and I forgot my limit sign just because I'm out of space here, 2 minus 1 over root x squared, which equals 4. So now I can say the limit of f to g, I'll throw it down here, hello, hello, what in the world just happened? Sorry, I had a little glitch there. F over g would be 1 over 4, which is what I believe I called from the get-go. So transitive helps, but there's so many different ways to do these problems. Last thing, sequential search ties in, we go in order. So if I had looking up a letter starts with A and there's 26,000 words, I just go number 1, number 2, number 3. Binary search means go half. So right in the middle at 13,000. Is it bigger than less? It's less. Go half again. Dot, dot, dot. And it's just it's a computer term that just solves a problem in much, much shorter amount of time. So this ties in with rates of growth and things like that. We're not going to get too into it. I did want to make sure you guys were aware. So that is it for now. My computer's glitching. I might just shut off. Nope, I got it. So I'll be able to say happy mathing.